Welcome back to the deep dive. Today we are strapping in for a cosmological journey that really challenges one of the most foundational ideas in
The
science.
cosmological principle, the idea that the universe is, well, basically the same everywhere you look.
Exactly. And we're talking about a major, very robust discrepancy that's been found in new radio surveys. It suggests the universe might have a kind of speed limit, and we might be breaking it.
It's a fascinating problem.
So our mission today is to unpack why the motion we see in the universe seems totally inconsistent with our cosmic standard.
And that standard, of course, is the cosmic microwave background, the CMB.
Right. Think of the CMB as the universe's own perfect speedometer. It has this tiny temperature variation at dipole.
Which is almost entirely attributed to our solar system's motion. We're just cruising along at about 370 kilometers per second.
And that motion gives us an expected deviation, a yardstick. It's called the kinematic source count dipole.
Or DUDX board, yeah. It's the baseline.
Okay, so we have this clean prediction from the CMB. It tells us exactly how fast things should appear to be moving from our perspective.
It should.
But when astronomers actually use these huge surveys to count things, radio galaxies, quasars, they find something way off.
A massive deviation. They've measured a dipole that is simply too large.
We're talking discrepancies up to 5.7 sigma in some cases. It's a great speed mismatch.
And what's so interesting here is that this mismatch might have been hidden, or at least confused, by a statistical error for years.
An error in the counting.
In the assumptions, yeah. Historically, cosmologists just assumed sources were scattered randomly, following a Poisson distribution.
Which works if you're counting, what, simple dots on a page?
Exactly. But when you look at modern high-resolution radio surveys like LOTSS DR2 or even the older NVSS, sources are clumpy.
They're not individual points.
No, they're extended galaxies, they're clusters. And treating a whole group as just one point introduced this huge error called overdispersion.
So the big breakthrough, and this is really the key, was to change the statistical model.
It was. Instead of Poisson, the new analysis uses what's called a negative binomial distribution.
If the old way was counting raindrops, this new way is counting the whole puddle.
That's a great way to put it. It properly accounts for that underlying clumpiness in the data.
So armed with this better tool, what did they find when they re-examined the best survey data we have?
The result is stunningly robust. They combined the most stable wide-area surveys, NVSS and RACS low, with the deepest one, LOTSS DR2. And the analysis found the measured source count dipole is about 3.7 times larger than what the CMB predicts.
Wait, hold on. 3.7 times larger.
That's right. And statistically, it's a 5.4 sigma finding.
5.4 sigma. That's well past the gold standard for a discovery. Is it possible this is still just some systematic error we haven't found?
That is the crucial question, of course. But the consistency makes it very hard to dismiss.
It's not just the size of it.
No, it's the direction. This excess dipole, this extra motion, points almost perfectly in the same direction as the CMB dipole. It's aligned within just 16 degrees.
Wow. Okay, so for random errors across different surveys, different frequencies, for them to all line up like that.
It's extremely unlikely. It's tough to argue it's just a coincidence that mimics a real cosmological signal pointing exactly where the CMB says we're moving.
So if we take this seriously, what does it mean for the big picture?
Well, it directly challenges the cosmological principle. We have to consider a couple of things. First, maybe we're in a huge local bulk flow, a vast region of space moving much faster than our standard model allows. Or the contamination from local sources, a kind of clustering effect, is just much, much greater than we ever anticipated.
But I know people are always checking for systematic effects, things like flux density calibration.
Constantly. But the fact that this magnitude and direction shows up across multiple independent radio surveys and even aligns with older infrared quasar studies, it really suggests this is not just noise.
So what does this all mean for you listening right now? This challenges the whole idea that we're not in a special place in the universe if it really looks different depending on which way we look. What does that say about our cosmic address?
It confirms we have to look closer. The future of really understanding this dipole lies with the next generation of massive sky surveys, like the Square Kilometer Array, SKA, and the EMU survey. They'll give us the data to resolve this, but until then, we have to face it. Either our standard model is missing a huge chunk of motion, or the cosmological principle itself isn't the whole story.